As companies look to outsource more and more of their chip manufacturing efforts to non American soil, America has grown increasingly concerned with the security risk that putting intellectual property on foreign soil brings. There have been many different types of attacks, including reverse engineering and IP piracy, developed with the intention of stealing valuable information. Logic locking has been a crucial method developers use to prevent this IP theft.
Many solutions have been proposed in response to the worries of malicious threats, such as insertion of extraneous hardware and stealing of IPs. Some of the solutions proposed do not cover the security at all of the bases of the manufacturing process of an IC. Such steps include manufacturing at the foundry level, SoC integration, testing of the IC, and malicious user tampering. For example, here are some proposed solutions and what they cannot ensure security at. IC metering, which cannot ensure security at the foundry level. Watermarking, which cannot ensure security at the foundry level, SoC integration level, and testing level. IC camouflaging, which cannot ensure protection at the foundry level. And split manufacturing, which cannot ensure security at the SoC integration level, testing level, and the user level. However, there is one process that aims to cover all the bases: logic locking. There is one problem with logic locking and the rest of the solutions. There has been a recent attack developed to debunk the security of these implementations called an SAT attack. Due to this attack method, there have been revisions and newer proposed solutions in order to combat against such attacks. The specific process of logic locking we will be covering today is SFLL HD0.
Logic locking is a hardware security technique designed to protect integrated circuits from unauthorized usage, reverse engineering, and intellectual property theft. By embedding configurable logic that requires a secret key, it ensures the integrated circuit operates correctly only when the key is applied. To implement logic locking, a functionality stripped circuit, or a FSC, is to be created in order to obfuscate the behavior of the chip itself. What the FSC does is that it creates certain logic inside of an output gate that modifies the result, causing erratic behavior. And in order to fix the problem, a restore unit is required. A restore unit will restore the functionality of the circuit only whenever a protected input pattern, or PIP, is applied.
Now let us get on with the processor attack. Alright, the demo we will be showcasing will demonstrate the safety of logic locking against SAT attacks. First, we will be showcasing the attack on two trial circuits. The first will be a very simple circuit called C17. This will show that the attack does what it is meant to. To preface, C17 is a very simple circuit. Because of this, the SAT attack will be able to crack the logic locking process. However, this is just a showcase that the SAT attack does work. Also to clarify, C17 has already been logic locked. To showcase that it has been logic locked, we will first show that the logic locked circuit is equivalent to the original circuit. Alright, now that we have verified that the two circuits are indeed equivalent, let us do the SAT attack on the circuit. Here is the output of the SAT attack. As you can see, the circuit was very simple, and because of that, this SAT attack was able to be successful in a very short time. For the second attack, we will be doing this on a more complex circuit to showcase the more safe nature of logic locking. The circuit will be of C432. We will once again showcase that the original circuit and the logic lock circuit are equivalent before doing the attack. Once again, we'd like to preface that the circuit has already been locked before doing this trial. As you can see here, the key is 36 bits. Hopefully this will ensure that C432 is that much more complex than C17. Alright, they're equivalent. Let's proceed on with the attack. As you can see, the attack takes many iterations. We once left this attack running for a couple hours before calling it quits. This hopefully gives a glimpse at how secure the process is. For the final demo, we will be showcasing a more realistic use case of logic locking. Hopefully, all 426 students should be familiar with the Ariane processor, which runs on a RISC-V architecture. We will logic lock a certain part of the processor, which will make it so certain functionalities are not available unless the correct value is given. Here is the processor, and here's the logic locking implementation, as well as 2 correct keys that are similar. For time's sake, we have pre-compiled versions of both the incorrect and correct key, and we'll be showcasing the difference in the outputs between the two. First up is the correct key. As we can see, it's just normal instructions all the way through, showing that it's a normal processor in working order. Here is the incorrect key, and as shown, there's an exception that occurs because the incorrect key makes it so that certain functionalities are stripped. Furthermore, the key for something like this processor is 32 bits, which, while a little smaller than the 36-bit C432 key, is actually probably a little more complicated, and is still very large, showcasing how difficult launching an attack against the circuit would be.